Before I start the podcast, I want to ask you for something. And that's that if you have any ideas for future episodes, or you have any questions about any of the material I've covered, or maybe you have ideas for guests to come on to be interviewed, send me an email. My email is sam@mcatbasics.com. Let me know what your idea is. And if I do make a podcast or do an interview on that topic, I will definitely give you credit for that. And if you want, you can actually leave me a voice message. I'll leave a link in the show notes to do so. All you got to do is follow the link and then click the record button and just record your voice. And then in that way, I can actually feature your voice directly on the podcast if you want me to. All right, now on to the show.
Welcome to the MCAT Basics Podcast, brought to you by the physicians at Med School Coach. Each week, Sam Smith breaks down high-yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host, Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast covers aromatic compounds. I'm going to start by talking about what an aromatic compound is and how to determine if a compound you're looking at on the MCAT is aromatic. I'll also mention how to determine if a compound is anti-aromatic. Then I'll talk about the properties of aromatic compounds and polycyclic versus heterocyclic aromatic compounds. And then I'll touch on a few common aromatic molecules that you should just be familiar with. And then finally, I'll discuss aromatic rings in biology. This material is going to show up on 2 out of the 4 MCAT sections. That's going to be the biochem section as well as the chem-phys section. So with that said, I hope you find this podcast helpful in your studies, and good luck to those of you who are taking the MCAT very soon. So the first thing I want to do here is define an aromatic compound. So an aromatic compound is a compound that contains one or more rings with pi electrons that are delocalized all the way around the ring or rings. This delocalization of electrons makes a molecule much more stable than it would normally be. Now, I kind of want to break that definition down a little bit because it's kind of complex. I'm going to break it down into 2 pieces. The first part of that definition says that an aromatic compound is a compound that has one or more rings. So hopefully you're somewhat familiar with what a ring structure looks like. Basically, it's a bunch of carbons or other elements that are all bound together to form a ring. They're all connected to each other, to form almost like a circular ring. That's pretty self-explanatory. Now, the other part of this definition is a little bit less self-explanatory, and it says that there are pi electrons delocalized all the way around the ring. So first off, pi electrons are electrons that are in a pi bond. So either a double bond or a triple bond. And there's a little bit more to it than just that as the definition for what a pi electron is. But for the MCAT, just think about pi electrons as being in either double bonds or triple bonds. I think that's good enough of an understanding to have just for the MCAT. Now, delocalization means that these electrons can essentially move around the ring kind of wherever they want to go. They're not found in a specific point around the ring. Again, they just kind of, move around. They can be on one side or they can be on the other side, or they can be on the bottom or the top or each side. They can kind of go wherever they want. They're delocalized. So overall, you can picture an aromatic compound as a compound that is a ring structure with some double bonds in it. That's kind of the most basic view of an aromatic compound. And that's actually exactly what benzene is, which is kind of the most simple aromatic compound. Now, it's important to understand how to determine if a compound is aromatic or not. Like, if the MCAT was to give you this drawing of some molecule, and it says this is some new drug molecule, and you see it in a passage, blah, 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 and then it asks you to determine if this compound is aromatic or not, it's really important to understand how to do that. With that said, there are a few criteria that a molecule must fit into in order to be considered aromatic. One of these criteria is called Huckle's rule, and that's part of what I'm going to talk about next. So in order for a compound to be considered aromatic, it needs to meet 3 criteria. I've already talked about 2 of these, and then the third is a new one. So, number one, it has to be cyclical. It's got to be a ringed structure. Number two, it's got to be fully conjugated. In other words, every atom in the molecule has to be connected to a double bond or to an atom that has a lone pair of electrons. And then the third criteria is that the compound has to fit Huckel's rule. So, Huckel's rule actually comes from the classic novel Huckleberry Finn, and it's also called the 4n plus 2 rule. And it says that in order for a compound to be aromatic, the molecule must have a certain number of pi electrons within a closed loop of parallel adjacent orbitals. Now, that's kind of the definition. What's more important to know is how you use that rule. Essentially, in order for a compound to be aromatic, the number of pi electrons that it has to be equal to 4n plus 2, where n is any integer. In other words, if you plug in 1, 2, 3, 4, 5, 6, 7, etc. into that equation, the number of pi electrons must be equal to one of those numbers. So taking the first three integers, 1, 2, and 3, an aromatic compound has to have either 6, 10, or 14 pi electrons. Now that obviously brings me to the next point, which is how do you determine the number of pi electrons in a molecule? Well, there are two different things you need to consider here. Number one, the number of double bonds in the ring of the molecule, and number two, the lone pairs of electrons in that ring. So each double bond has 2 pi electrons in it. So first off, you can just count each of the double bonds in the ring of a molecule and then multiply that by 2, and that will give you how many pi electrons are in the double bonds of a ring. And then you got to look at the lone pairs. And when we're talking about lone pairs, we're talking about atoms that are in the ring structure. So this has got to be an atom in the actual ring. It's got to be like a nitrogen or an oxygen that is actually in the ring. Now, if one of the atoms in the ring has a lone pair or 2 lone pairs of electrons, that counts as 2 pi electrons. Basically, for each atom in the ring that has a lone pair or 2 lone pairs, it adds the same amount of pi electrons that a double bond does. So for a nitrogen in the ring that has a single lone pair of electrons and an oxygen in the ring that contains 2 lone pairs of electrons, those are only each contributing 2 pi electrons. So overall, you determine the number of pi electrons in the double bonds in a ring, as well as coming from the lone pairs. You add those together, and if that number is equal to 6, 10, 14, etc., using this 4n plus 2 rule, then that compound is aromatic. That is, of course, if the compound is cyclical and also fully conjugated. So that's the criteria for a molecule to be considered aromatic. Now, you should also be aware that there are compounds that are considered anti-aromatic. Basically, they resemble aromatic compounds, but instead of being extremely stable, they're extremely unstable. And like aromatic molecules, anti-aromatic molecules need to fit 3 criteria. Number 1, they got to be cyclical. Number 2, they have to be fully conjugated. But number 3, they don't fit Huckel's rule. In fact, they fit the 4n rule. In other words, these have 4, 8, 12, etc. pi electrons. Now, to determine if a compound is anti-aromatic, you would literally do the same thing that we did for aromatic compounds, that being count the number of pi electrons in the double bonds of a ring, as well as the pi electrons that come from lone pairs within that ring. And then in this case, after you add up the total number of pi electrons, it has to be a multiple of 4. And if it is a multiple of 4, then the compound is anti-aromatic. And just to reiterate, aromatic compounds are typically super stable, and then anti-aromatic compounds are super unstable, and then a compound that is non-aromatic, which means it doesn't meet the 3 criteria for either of these cases, is going to be somewhere in the middle. It'll be just, kind of stable. If we're talking about aromatic, anti-aromatic, and non-aromatic in terms of Cheerios, aromatic Cheerios are essentially going to be like the brand name Cheerios, right? Those are the best. They taste the best, obviously. And then the non-aromatic version is going to be the Kroger brand. So it's not quite as good as the brand name Cheerio, but it's close. And then finally, anti-aromatic is going to be like those organic Cheerios that I don't even know what they're made out of. I think cardboard. Is cardboard organic? I don't know. They taste horrible, and They don't absorb milk the same as a normal Cheerio. And so that's kind of the anti-aromatic case. The anti-aromatic's the worst. It's super unstable. All right, the next thing I want to get into here is actually something that comes directly off of the AAMC content outline for the MCAT, and that is polycyclic and heterocyclic aromatic compounds. What I'm going to do is I'm just going to define the difference between these. And then later on in the podcast, just throughout, I'll kind of bring each of these up as I explain, different concepts as well as different examples. All right, so I'll start with polycyclic aromatic compounds. These are aromatic compounds that have multiple aromatic rings in a single compound. And these things can be super massive. For example, ovalonine is a polycyclic aromatic compound that has 10 interconnected six-member rings. If you go Google an image of ovalonine, you'll see it's just this massive compound that actually looks a little bit like an oval, and maybe that's why it's called ovalonine. Heterocyclic aromatic compounds, on the other hand, are aromatic compounds that have something other than carbon in the ring. I talked about this a little bit when we were talking about lone pairs in aromatic compounds, like in the ring of an aromatic compound. And there's really two atoms that show up in these aromatic rings, that being nitrogen and oxygen. For example, furan is a five-membered aromatic ring that has one oxygen that is in that five-membered ring. And then a molecule called pyridine, which you're probably familiar with. It's a base that shows up in DNA, is a six-membered ring with a nitrogen being one of those members. Either way, heterocyclic aromatic compounds are aromatic molecules that have an element other than carbon in a ring. And also don't forget that these elements can add to the aromaticity of a ring, right? They can have pi electrons in the form of these lone pairs that are able to delocalize and are also pi electrons. So just kind of keep that in mind. Now, before I dive into the properties of aromatic compounds, I want to just go over some of the most common aromatic compounds to know. And really what you should do here is if I mention one that you're just completely unfamiliar with and you're like, shit, I don't remember what that looks like, just go Google it and then put it on a note card and memorize the structure as well as the name. That way, if you see it come up in a passage and somehow you need to understand the structure of that compound, you'll know what it looks like. So there are four different aromatic compounds that I want to mention here. The first of which is called benzene. This is basically the most simple or classic aromatic compound, at least in my opinion. It is a six-membered ring that contains six carbons and has three double bonds. Also, keep in mind that aromatic rings can be represented with that ring with a circle inside of it. So benzene can be represented by a hexagon with a circle drawn in it, or a hexagon with three double bonds. Either way, it's the same thing, it's benzene. The next aromatic compound that you should know is called toluene. Toluene is basically benzene with an extra methyl group on it. It basically looks like benzene, but with like a stick sticking off of it, that stick being a methyl group. The next molecule is called phenol. This is a benzene ring with a hydroxyl group attached to it. And keep in mind that this is fairly acidic. Basically, it can donate that hydrogen away, since the benzene ring can actually help delocalize the negative charge that's left on the oxygen once the acidic hydrogen leaves. Finally, the last compound that you should know is called aniline. This is a benzene ring with an amino group, NH2, attached to it. Also, don't forget that aromatic rings can be substituents. So when you have an aromatic ring that is directly attached to a molecule that has the substituent name phenol. On the other hand, when you have an aromatic ring that is attached to a methyl group, that then the methyl group is attached to a molecule, that is considered a benzyl substituent group. All right, so that's a little bit of naming. And as with all naming on the MCAT, really all you got to do is be able to recognize the names of different compounds. These might show up in passages and question stems, and you'd be expected to recall the structure from the name or be able to recall the name from the structure. So really, again, it's a recognition type game. You're not going to actually be writing the name of some molecule like you would on an OChem test. What I'm trying to say is that naming on the MCAT is going to be a whole lot easier than it was in OChem class, like on OChem tests. But again, if you don't know these compounds that I just named, make sure you do know them, put them on flashcards, and get them memorized. Now, the next thing I want to talk about here are the different properties of aromatic compounds. There are four properties in particular that I want to talk about here. I want to talk about the physical properties of aromatic compounds. I want to talk about their reactivity or their stability. I want to talk about their fluorescence. And then I want to talk about a little bit of a special case, and that's that nitrogen containing heterocycles are basic. Physical properties. So, in general, aromatic compounds are fairly nonpolar and therefore insoluble in water. And this next one is more of a chemical property and is really for your interest only. But aromatic compounds, especially the polycyclic type, tend to be pretty carcinogenic and pretty toxic. Now, why is that? Well, these polycyclic aromatic compounds are highly lipid soluble, and thus, when you eat them, they are readily absorbed by the lymphatic system. So they make it into circulation pretty easily. And then the mechanism of toxicity is considered to be the interference of the function of cellular membranes, as well as with enzyme systems that are associated with the membrane. That's from one paper. Another paper says, quote, metabolism of some polycyclic aromatic compounds also generates reactive intermediates that are capable of forming covalent adducts with nucleic acids, leading to genotoxicity, end quote. So aromatic compounds are nonpolar, insoluble in water, and can be very toxic. Reactivity. So this part's pretty simple. I kind of already mentioned it. In general, aromatic compounds are really stable, and in fact, they're actually less reactive than alkenes, which they themselves are very stable and very unreactive. So that's saying something. So overall, aromatic compounds are very stable and not very reactive. Fluorescence. Now, this is something about aromatic compounds that I didn't know before, but I think it's pretty interesting, and I think it's something that's important to keep in mind that these compounds can do, and that's pretty unique to them. So many aromatic compounds actually fluoresce when they are excited by UV light. In other words, when you shine UV light on many aromatic compounds, they actually give off light themselves. For example, if you expose phenol to UV light, it gives off violet light and it looks violet. On the other hand, some of the bigger polycyclic aromatics can be orange or red or even green when they are exposed to UV light. Now, why is this the case? Why are aromatic compounds able to fluoresce? And this question was really interesting to me, and I did quite a bit of research to try to really understand it. And let me just say this is a really complex question. In short, the reason that aromatic compounds are able to fluoresce is because they have a bunch of conjugated pi electrons. These electrons have an easier time being excited by UV light, meaning they more easily are able to jump from one energy level to a higher energy level. And then once these excited electrons fall back down to a lower energy level, they emit photons, and that is fluorescence. So it really goes back to the fact that these pi electrons in aromatic compounds are able to be excited easier. Thus, more frequently, these electrons are excited. And when they're excited, they have to eventually jump back down to ground state. And when they jump back down to ground state, they emit photons, and then the process repeats. And because they're able to do that so easily and so much, they fluoresce. A great example of how this fluorescence is used in science is in qPCR machines. So qPCR, also called real-time PCR, uses these fluorescent probes to visualize the progress of a PCR reaction. And the active ingredient in these probes is fluorescent dye. Now, when you look at the structure of many of these fluorescent dyes, if not all of these dyes, they contain at least one aromatic ring. And on top of that, many of them are polycyclic aromatic compounds. And that's why they fluoresce. Pretty freaking sweet. Special case. All right, so the last property that I want to talk about here is kind of a special case. and that's that nitrogen containing heterocycles are basic. So that's to say that nitrogen containing heterocycles, which are basically aromatic rings in which there is a nitrogen within the ring, can pick up and bond to hydrogen atoms or protons in their environment. They can act as bases. Now, with that said, I should mention a little bit of a caveat. The only case in which a heterocyclic aromatic nitrogen, which is in a aromatic ring, cannot be basic is when the lone pair of electrons on that nitrogen participates in the conjugated pi system. But really, the takeaway message here is that when you see a nitrogen atom in an aromatic ring, think base, because the compound is probably basic. All right, so that's it for the 4 properties of aromatic compounds that I wanted to mention. The next and last thing I want to talk about here is aromatic rings in biology. Can't get into a hospital or doctor's office to do shadowing? Well, you're in luck. A 4th-year medical student and I just produced a virtual shadowing video series that is also a podcast. The idea here is to help pre-meds get some kind of clinical experience during the COVID-19 pandemic, since it's pretty hard to right now. I obviously have no idea how admissions committees are going to view this. I don't know what they're going to say if you put it on your med school application, but I imagine that it's only going to help in that it's better than nothing. Throughout the recording of the series, I learned a ton, and I think you would too. So if you're interested, search virtual shadowing in your podcast app or visit shadowing.medschoolcoach.com. So there are so many good examples of aromatic rings in biology. There are aromatic rings in amino acids. There are aromatic rings in purines and pyrimidines, which are in DNA. And they're even in the electron transport chain, where they're able to carry and pass off electrons. So really, altogether, aromatic compounds play such a huge role in biology. Now, what I want to do here is just take a little bit of a deeper dive into each of those categories that I mentioned. I'll start with amino acids. So there are 3 amino acids that have aromatic rings in them. The first is tryptophan, that has 2 aromatic rings. Then is tyrosine, that has a single aromatic ring. And finally, we have phenylalanine. That, like tyrosine, has a single aromatic ring. Now, something that's interesting about these particular amino acids is that they appear frequently at protein-protein binding sites that are on proteins. And this is partially because of what are called cation pi interactions. Essentially, the aromatic rings in these aromatic amino acids can interact with positively charged amino acids. Now remember, at physiological pH, there are 2 positively charged amino acids. That's arginine and lysine. So basically, these 2 positively charged amino acids see aromatic rings on other proteins and say, damn, the back of your ring looks ridiculous. And then they form these cation pi interactions, which are basically just strong intermolecular forces that keep these 2 groups close together. And thus, these 3 aromatic amino acids appear frequently at protein-protein binding sites that are on proteins. All right, the next thing that I want to talk about here are purines and pyrimidines. These are the bases that show up in our DNA and RNA. So purines are heterocyclic aromatic compounds. This is cytosine, thymine, and uracil, or C, T, and U. So these are single-ringed aromatic compounds that contain some other element than carbon within the ring, and in all of these cases, that element is nitrogen, i.e. these are called nitrogenous bases. You've probably heard that before. Purines, on the other hand, are polycyclic aromatic compounds. These are compounds that have multiple, in this case, 2 rings that are attached to each other, and these 2 rings are both aromatic rings. Also, like pyrimidines, these aromatic rings contain nitrogen within them, and they too are considered nitrogenous bases. And of course, the purines are adenine and guanine. Now, what does that term nitrogenous base remind you of? Well, I hope it reminds you of what I talked about earlier, the fact that nitrogen-containing heterocyclic aromatic compounds are basic. And these compounds, purines and pyrimidines, are basic. they can take up protons or hydrogen in their environment and bond to them, their bases. So that's purines and pyrimidines. The last type of biological aromatic molecule that I want to talk about is a few different molecules that show up in the electron transport chain and throughout metabolism. That's going to be ubiquinone, NAD+, and FAD. Now, what property kind of ties together those three molecules? Well, really, it's that they're good electron carriers. And what makes them good electron carriers? Well, as I'm about to talk about, they're good at being oxidized and reduced. So I'll start with ubiquinone. Ubiquinone is an aromatic molecule that acts as an electron carrier within the electron transport chain. Ubiquinone is able to accept two electrons and becomes its reduced form called ubiquinol. Then it can travel to a different part of the electron transport chain where it passes those electrons off and becomes its oxidized form, which is again ubiquinone. NAD plus and FAD perform fairly similar roles in the electron transport chain as ubiquinone. However, instead of carrying electrons within the electron transport chain, they actually carry electrons to the electron transport chain. NAD plus is a heterocyclic aromatic compound, and then FAD is a polycyclic aromatic compound. When NAD plus gains two electrons, it becomes reduced and is called NADH. And then on the other hand, when FAD is reduced, it as well gains two electrons and becomes NADH2. Now, what I want to mention here, and something that's kind of interesting, is how the aromatic rings that are contained within NAD+, FAD, and ubiquinone contribute to their ability to carry electrons and be easily oxidized and reduced. So first off, what makes a compound a good electron carrier? Well, basically the molecule has to be able to lose and gain electrons easily and remain stable throughout that process, right? Because a lot of molecules, if they lose two electrons, they're going to be very unstable. Or if they gain two electrons, they're going to be very unstable. And that's not good, right? Biology wants stable. And that's where the aromatic ring comes in. An aromatic ring has, as we know, extra stability. So that's what's able to actually stabilize the molecule once it loses electrons. So take NAD plus, for example. NAD plus, if it were not aromatic, would not be a very stable molecule. But that aromatic ring within the molecule helps stabilize it. And then once it gains two electrons, it becomes NADH, which is not aromatic, but is still a fairly stable molecule. So just to kind of reiterate and summarize what I'm saying, the aromatic rings within ubiquinone, NAD+, and FAD help stabilize them. Thus, that makes them easily able to reduce and oxidize, and therefore they are good electron carriers.
At Med School Coach, we know that getting into medical school is hard. In fact, 60% of pre-meds who apply to a medical school don't even get accepted. And if you want to get accepted into a top medical school, it's even harder. That's why more students than ever are turning to MCAT tutoring by Med School Coach. Our tutors are all 99th percentile scorers, have been through rigorous training, and can help raise your MCAT score by 12 points or more. You need every competitive advantage you can get to get into med school, so why not get one-on-one tutoring from Med School Coach? Our expert team will create a custom program just for you and help you master MCAT content where you need the help most. You'll raise your MCAT score. We guarantee it. Visit us online at medschoolcoach.com and use offer code PODCAST10 to save 10% up to $400 on a Med School Coach MCAT tutoring package. You can achieve your medical school dreams, and Med School Coach can help.
So that is it for the Aromatic Compounds podcast. I want to kind of just leave you with a summary of everything that I've talked about. So aromatic compounds are compounds that meet three criteria. Number one, they must be cyclical. Number two, they have to be fully conjugated. In other words, every atom in the molecule that is cyclical has to be connected to either a double bond or an atom with a lone pair of electrons. And third, they need to fit Huckel's rule. The number of conjugated pi electrons has to be equal to 4n plus 2, where n is some integer. Aromatic compounds are very stable And when exposed to UV light, they fluoresce. And then finally, in biological systems, they are good electron carriers because they're able to easily accept and give away electrons and remain stable throughout that process. All right, so that is it. As always, if you like what we do, please leave us a review on iTunes. It helps us in the rankings and it helps us reach more students. If you have any questions, comments, or concerns for me, please email me. Again, my email is sam@mcatbasics.com.
Each episode of MCAT Basics is brought to you by Med School Coach. To access Med School Coach services, including MCAT tutoring and medical school admissions advising, visit our website at medschoolcoach.com. Good luck as you prepare for the MCAT, and we hope you tune in again next time.